recording? Okay, now I'm recording. Okay, so so far we have 2 silver nitrates and we have calcium chloride, and now we've decided that we have 2 silver chlorides to go with this. And so that balances out the silver nitrate, that balances out the calcium chloride, and that balances out the silver chloride, and I look at the calcium nitrate and that's balanced. So this whole thing now is balanced. So we have 2 silvers, we have 2 silvers, we have 2 nitrates, we have 2 nitrates, we have 1 calcium, I have 1 calcium, I have 2 chlorines over here on the left, I have 2 chlorines on the right. Y'all see that? Okay, so that's balanced. So when we're doing polyatomics, make sure that you keep them together. Okay, and so let's do one more and then we're going to move on from balancing. Okay, we'll do one more balancing equation because we got to move on. Remember, this is an online course. You need to do a lot of work on your own, which means download Google Worksheets and make sure that you are doing lots and lots of practice. Okay, so let's do one more. So let's say that we had, let's say, how about let's do sodium carbonate plus barium chloride. All right, and what we're going to end up with is barium carbonate plus 2, well, I'm giving it away, but we're going to end up with sodium chloride. All right, and I'm going to show y'all probably on Monday. I'm going to show you how to make predictions. In other words, on Monday, right now we're just balancing equations, okay? But one of our essential skills is going to be, given these 2 things, predict what you get. In other words, you don't have the right-hand side. This is where we're heading. Right now I'm just giving you an unbalanced equation. So let's balance this. So I look here and I see sodium carbonate. This is sodium carbonate. How do I know this is carbonate? Because I memorized my polyatomics on page 66. That's sodium carbonate. This is barium chloride. How do I know it's chloride? Because it's just the element. And this is barium carbonate. Remember when I said don't bust apart your polyatomics, keep them together, right? And so sure enough, it is together. And this is sodium chloride on the right hand side. Okay, so always keep in mind you need to be able to name them. All right, now it's not part of balancing, naming it, but naming is important. And so I look here and I see sodium carbonate, and I look over here and I see, you know what, I got 2 sodiums. I think I better put a 2 over here for those 2 sodiums. See that? For the 2 sodiums. And I look here, remember what I said, we're not going to balance it as 1 carbon and 3 oxygens. What we're going to do here is we're going to balance it as a carbonate. And so I look over here and what do I see? I see 1 carbonate. A carbonate's a CO3. By the way, don't you be looking at that 3 and saying you have 3 carbonates. That 3 is for the oxygen in the carbonate. That 3 is for the oxygen in the carbonate. You have just 1 carbonate. So the carbonates are balanced. So we have 1 carbonate on both sides. We have 2 sodiums on both sides. So the first molecule is balanced. And now we look at the second one and we say barium. We got 1 and we have 1. So the bariums are good. We have 2 chlorines and I have what? How many chlorines do I have there? I have 2, right? Because there's 2 of everything. There's 2 chlorines. And so this guy is now, let's make sure that it's balanced, and we got 2 sodiums, 2 chlorines, we got the barium carbonate, and the whole thing is now balanced. Okay? So like I said, some of this is probably about half or 70% of this is following procedure as far as balancing goes, and the other 30% is pattern recognition. pattern recognition and following a couple of rules. Like, for instance, don't bust up your polyatomics, for instance. These little rules like that. Okay, doing diatomics and atomics, do them last. All right, so that's balancing. All right, let's get into the math part. All right, here comes the math. Balancing is usually something most people can figure out over time. It's the equations part that we're going to get into. Now, first off, let's say we have this balanced equation. Here is a balanced equation. It is my favorite equation, and like my children, I do have favorites, and so I do have a favorite balanced equation. In case you're wondering, it's my little girl. She's my favorite. Now, this is my favorite equation. It's my favorite equation because it's got lots of stuff to it. Now, when you look at this equation, what is this telling you? It's saying I'm going to take four aluminum atoms, as a matter of fact, and I'm going to react with 3 oxygen molecules, and I'm going to get, after I do that, I'm going to get 2 aluminum oxide compounds. Okay, this is what it's telling you. I mean, essentially, a balanced equation is a recipe. It's no different than saying, if I take 2 cups of flour, 3 eggs, and a stick of butter, I get a cake. Okay, it's the same thing here. I take 4 aluminums, 3 oxygens, and I get some aluminum oxide. I get 2 of them, as a matter of fact. Okay, now, the problem here is if we said 4 atoms plus 3 molecules gives me 2 compounds. Atoms and molecules are really small, and it would be very inconvenient to count out 4 atoms of aluminum and 3 molecules of oxygen. For one thing, if we're making aluminum oxide, and by the way, aluminum oxide is sandpaper, in case you ever wondered what sandpaper is made out of, it's usually aluminum oxide. All right. And so if I want to make sandpaper, I'm going to need a lot more than 4 atoms and 3 molecules to make tons of aluminum oxide because, well, molecules are small. Okay, you're going to need a lot of them. So what can we do? Well, I'm not going to count out 4 bazillion atoms and 3 bazillion molecules to make 2 bazillion aluminum oxides. I'm just not going to do that. It's not practical. Okay, so what we got to do is we've got to take a way of taking counted, these are counted, 4 and 3 is counted, and we have to go to something that I can weigh out. Because what do we do in the lab? In the lab, we have a scale and a dish, and by the way, you always subtract out the dish or the container, right? And you throw your stuff on there, and that's what you react. Okay, so many grams, 14.09 grams, so many grams. This is what we do in the lab, right? We don't take a pair of tweezers and count out O2 molecules one at a time. Okay, we don't do that. So we have to have a connection between counted and weighing out. Now, if you've ever worked in a warehouse, and most people have not, but I've worked in a warehouse, and one of the things you have to do is one thing that you have to be able to do is be able to count large quantities of things in a warehouse, because you don't want to sit there and count them out. And so let's say you have a bin, a very large bin. I used to work in operations management, and here I am out on the floor with my tie on. Here I am. There I am. Okay. And so we have to count all these bolts. These are all bolts, by the way. A bolt looks like this. It's got a thread on it. It's got a head on it. It's got you got a lot of bolts in this big bin. And I got to set someone over there, and we got to count those bins, because inventory is about taxes, and the government wants their taxes, so they want to know how many bolts you have down to the last one. There's many thousands of bolts in this bin, if you can imagine. This is to scale. So how would we count out the bolts? Well, I could set someone down. I can set one of my employees down, and one day you may very well manage people as a professional, and he or she is sitting here counting out one bolt at a time. And how do you think that person feels counting out one bolt at a time? Not very happy, right? So how would you count out the bolts quickly? Well, what you do is you take one bolt and you put it on a scale. And you say one bolt is 2.00 grams, and that's a bolt. All right? And then you take off that bolt, you go grab a forklift. Okay, now this person goes and grabs a forklift, and they're very happy now because they get to ride the forklift. And they put this stuff on the scale. Okay, they put it on the scale, this whole bin full of bolts on the scale. All right, and now the scale tells you that it weighs 14,278 grams. That's what the scale says. And of course, you always have to subtract off your container, just like we did for lab 1 and lab 2. You always have to subtract off your container. And so we subtract off the container, we had 14,278 grams. How many bolts do we have? Well, we already decided that it was 2.00 grams per bolt. Well, wait a minute now. Now look, this is a conversion. This is something over something. This is dimensional analysis. So you say, you know what? I start with my measured number, 278 grams. And I say, you know, a bolt is 2.00 grams. Grams cancel, right? And I end up with 7,000. I'm going to try to do the math in my head today. 1, and that would be 3, and that would be 9 bolts. There it is. Ta-da! It took me longer to go get a forklift and put it on the scale than actually figure out how many bolts I have. Rather than having someone sit there and count out 14,000 bolts. And just an FYI, if you ever do work in manufacturing, a typical employee can count or do roughly about 5,000 operations per 8-hour shift. Between 3,000 to 5,000 operations per 8-hour shift. That's counting, sorting, sealing, moving, whatever. You know, that's how many they can do with their hands. And so it would probably take him or her 2 days to count out those bolts. But if you throw it on a scale, you can do that. Now, how is this going to work for what we're trying to do up here? Well, what we do is we say, you know what? Instead of saying 4 atoms of aluminum or 4 gazillion atoms of aluminum, we give it a special number. And what we're going to say to get there is we're going to have something called a mole. And we're going to say we have something called a mole, and we're going to say it's equal to 6.022 times 10 to the 23rd of anything. But usually we mean atoms and molecules. But a mole can be anything as long as it's 10 to the 23rd, 6.022 times 10 to the 23rd. And so where does this come from? What this comes from is that if we take 12.00, many zeros as you want, grams of carbon 12, it will be equal to 6.022 and a lot of decimals behind it times 10 to the 23rd carbon atoms. Okay, so now we have a way of going from grams to atoms and something called a mole. Now, atoms is counted. You count out the atoms. Now, 6.022 times 10 to the 23rd is an awful lot of atoms. Matter of fact, in a mole, There's not even that many grains of sand on the entire planet. There's not that many. 10 to the 23rd is a huge number, but atoms are small. Now, because we did this with the 12 grams of carbon 12, if you look on your periodic table, you will see for carbon, you will see that it looks like this on the periodic table. And I told you the other day that this was the weighted average of all the isotopes of carbon, right? Most of them being carbon 12. But because we defined this thing called the mole in terms of carbon 12, and we said carbon 12 was 6.22 times 10 to the 23rd carbon atoms, and it was carbon 12, this now becomes 12.001011 grams carbon for every mole carbon, because of the way we define the mole as being 6.022 times 10 to the 23rd, and we said 12.00, as many zeros you want to go out, of carbon 12 is equal to that same quantity. Because of that, the number below the element is now however many grams 1 mole of that substance weighs. So if you look underneath oxygen, you will see if you round it, and we always round the 1 decimal if we can, grams oxygen for every mole. Oxygen, if you look underneath aluminum, you will see 27.0 grams aluminum for every mole aluminum. And if you look underneath chlorine, chlorine is 35.5, and so you say 35.5 grams chlorine for every mole chlorine. And you may say, well, why do we go through all this trouble? Because now we can go back over here to our previous situation over here, and so instead of saying 4 atoms of aluminum, we can now say 4 moles of aluminum. And if we have 4 moles of aluminum, then that would be 4 mole times 27.0 grams aluminum for every mole aluminum. And that tells me, let's see, what is that? It's 54, what is that? 54 be 108. That would be 108 grams aluminum that we need to throw on the scale. I can weigh out 108 grams. No problem. You want me to count out 4 atoms? I need some expensive equipment to do that. Okay, I can do it, but it'd be very expensive. It wouldn't be very practical. But if I wanted 4 moles of aluminum, I would weigh out 108 grams of aluminum. If I wanted 3 moles of oxygen gas, well, that would be 3 times 32, and that would be what? 96 grams of O2 that I would weigh out. And if I added up all of this over here, I would get 204 grams of aluminum oxide on the other end. So now I go from having to count atoms out to something I can throw on a scale and not worry about how many atoms I have anymore. I don't worry about how many molecules I have. All I care about is, go get me the bucket of aluminum and let me weigh it out on the scale. And I mix these things together, let it react, and I ought to get, so many grams of the product. Because that's really what you're after, right? You don't care about how many atoms there are. You care about how much it's going to take. So that's the whole point. If you've been reading ahead, and you should be, this is the whole point of the 6.022 times 10 to the 23rd per mole, otherwise known as Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd atoms or molecules per mole. And by the way, Avogadro did not come up with Avogadro's number. It's just named after him. I forget who actually came up with it. It was probably some English or German dude. It always is. So you have that. So we have our first relationship. Our first relationship is going to be this. we have 6.022 times 10 to the 23rd atoms or molecules per mole. This is our first relationship as far as stoichiometry, otherwise known as stoic. Let me make a better 23. Let me do that. 23. There it is. Okay? This is atoms or molecules per mole. Now, this in and of itself is not terribly exciting, but we have to be able to use it. All right, now, how do we use this? Anytime you have something over something, this is what? This is a conversion factor. This is a conversion. It's a conversion. This is the way you go from atoms to moles and mole to atoms or molecules. Okay, this is how you go in between them. This is no different than say 12 inches equals a foot. It is no different than saying 100 centimeters for every meter. It's no different. All this stuff, now you got to get this through your head. When we do these calculations in chapter 3, they're all big dimensional analysis problems. That's all they are. They're big dimensional analysis problems. And which means we have to make sure that whatever we do, we have to make sure that units are used, and we have to make sure that units cancel in everything we do. Remember what I said? This is a hard chapter, but I'm going to show you step by step. And so the first thing you have to do with everything here is make sure you're always using units. You always have everything labeled, and you always, when you have your final setup, that everything has to cancel. In other words, units have to cancel. If they don't cancel, something's wrong. All right, so that's my first relationship up there. Okay, so let's do some stuff with this. All right, so let's see. How many? Oh, let's see. How many aluminum atoms in 4.18 times, let's just 4.18 grams, let's not do that, mole aluminum. There you go. I got to make these things up on the fly. I don't have problems already made up. It's much more interesting to me if I make up the problems as I go along. Okay. All right, so we have this question here, and I want to know how many aluminum atoms are in 4.18 moles aluminum. All right, now here's your first thing that you're going to have to do. When you see number of atoms or molecules, all right, you will need 6.02 times 10 to the 23rd per mole. All right, anytime you see it. So let's go back to this previous page here. I had this is for atoms or molecules. All right, this is for atoms or molecules. This is what I call looking for key words or key factors. Now, we're just working on Avogadro's number. We're just working on a relationship of 6.22 times 10 to the 23rd per mole. But let's back up. Anytime you see the words number of atoms or number of molecules, you're going to need this relationship. If you don't see number of molecules or number of atoms, then you do not need this relationship. And that's important because sometimes we look at this stuff, especially Avogadro's number, and we look at this as being like pixie dust, this relationship. Do you know what pixie dust is? Pixie dust, you sprinkle it on something and it makes it all better. That's what pixie dust does. And so there is a tendency sometimes for folks to say, well, I can't quite figure out the problem, but if I throw in Avogadro's number, it'll make it all better. That's pixie dust. All right, now, so what we do want to do is we do not want to use this unless I actually see the words atoms or molecules in there. Now, do I see number of atoms or molecules? And I sure do. How many aluminum atoms? I see that. So I know I'm going to need that. Okay? And so that is a conversion factor, so I know I have that, and I already wrote it down. But you would have to automatically write it down. All right, so I already wrote it down. Okay, do I see anything else up here that I need? And you have to ask yourself when you do these problems, do I see anything else that I need as far as conversion factors? We haven't done anything else as far as conversion factors. So there isn't anything up there, but I'm going to tell you, especially on Monday, maybe even today, that there will be keywords, other keywords that we're looking for that are going to tell us that we need additional information. Okay, but we don't on this one. All right, so what do? I have everything I need, and so what we do is we draw a line, we draw another line. All right, what lives here? What lives there is my measured number. All right, this answers the question. Remember, we did dimensional analysis. The question always is, and I remember asking this question, where do I start? All right, where do I start? And that's a legitimate question. Where do I start? And I'll tell you, the answer to this is you always start with the measured number. All right, 6.022 times 10 to the 23rd per mole is a conversion factor. Anytime you have something over something, it's a conversion factor. So what do I have up here that is the measured number? And that would be this guy right here is my measured number. All right, that's my measured number. And so that's what we have to start this setup with. And so I say 4.18 mole aluminum. Now notice I have a unit and I have a tag. I have a unit and I have a tag. This is very important because you see the number there is not just 4.18. It's not just 4.18 mole. It's 4.18 mole aluminum. All of this is important. You cannot leave off anything. If you leave it off, you may or may not get it right. You might get it right, you might not get it right. And I tell you what, I don't know how y'all feel about this, but I don't like mights. I don't like might get it right. I like to know that I'm going to get it right. You see what I'm saying? Okay, so make sure that you always have the unit and you always have the tag. So what's up next? Well, if we're going to cancel units, if you remember from the dimensional analysis, what is next has to have the same units down here. Moles aluminum. That way we can cancel. Where do we have moles aluminum? We have it right up here. I just put it back in there, but there it is. And so we're going to use our 6.022 times 10 to the 23rd aluminum atoms per mole of aluminum as a conversion factor. And so this will actually go down here as written. Y'all see that? Now look, see? If you look, moles aluminum cancels, moles aluminum cancels. You see that? What are we left with? Aluminum atoms. What are we looking for? aluminum atoms. Now all we got to do is put it in the calculator. And I pull out my calculator, and I left it downstairs, wouldn't you know it. So I pull out my calculator, and I say 6.02 times, oh, what let's see, where's my 6.22, what did we have here, 4.18. That would give me 25.2, which would be 2.52. 2.52 times 10 to the 24th aluminum atom. There it is. If I put it in right, and I do believe I put it in the calculator right. Now, sig figs. I did sig figs on the fly, but this was 3 sig figs here. This was 4 sig figs here, so our answer should be 3 sig figs. By the way, significant figures always count and are always important no matter what you do. Alright, rules for multiplication is you go by least number of significant figures. Okay? Least number of significant figures. Alright, let's do another one. Can I do another one? Has everybody got this? Of course, you know, it's being taped, so at any rate. Alright, let's do another one. And so I want to know, Kaylin is left. Alright, let's see. So I want to know how many mole of sodium is 4.29 times 10 to the 24 sodium atoms. All right. And we'll make this the last problem. We'll wrap it up on this one, okay? Because I think we're nearing the saturation point on some folks. Okay, so we have a question here. So it says, how many mole of sodium is 4.29 times 10 to the 24th sodium atoms? Now remember what I said about these problems in chapter 3 and chapters after this as well. You have to ask yourself some questions. Now we only have one question to ask so far. There will be 3 or 4 that we're going to ask ourselves, but we only have one so far, and that is, do we see number of atoms or molecules? And the answer is, why, yes we do. I see a bunch of sodium atoms. So since I see that, I know that I'm going to have to write down, and I'm going to need it somewhere, I know I'm going to need this. How do I know I need this? Because I see sodium atoms over here. That's how I know. Okay, that's how I know. All right, that's how I know. So I have everything I need because I don't have any other questions that I can ask myself, and so I'm going to draw a line. I'm going to draw another line. Now, what's my measured number? This is my measured number. It's right here. So what do we do? We always go with what? Our measured number. We always start with our measured number. That's my measured number there. So I'm going to start with the measured number. 4.29 times 10 to the 24th sodium atom. All right. So what goes down here? Sodium atom. It's got to be sodium atom. Where do I see sodium atom? Right there. So I'm going to have to flip this relationship over to get sodium atom on the bottom. So we're going to say mole sodium for every 6.022 times 10 to the 23rd sodium atom. Oh, look what happened. You see that? Look what happened. Sodium atom canceled. I'm telling you, if you can set these things up, and the setup, you got to take your time on these setups. But if you can get all the units to cancel, you're on to something. and you can't help but get it right. So now we need to put this in our calculator, and I put it in my calculator and I go, what is that? That's 4.29, and that's actually 42.9. Let's go 42.9. I don't have my calculator up here. Bad. It's divided by 6.022, and I get 7.12 mole sodium. There it is. There it is. Okay, so it just has to make it into the calculator at this point after you do the setup. All right, so what do we have so far? We have for essential skills, always essential skills that we have to do. So far, what do we have for chapter 3? We have reaction types. You need to do that on your own. There's like 5 of them or something like that. Reaction types. We have balance equations. You need to practice for that, right? And now we have Avogadro's number, or we have 6.02 times 10 to the 23rd equals a mole. All right, and being able to use that. Okay, those are our essential skills so far. And of course, I should put down using in equations. All right. So those are my essential skills, and we will continue this on Monday. Do not take the weekend off. Make sure that you are working tons and tons and tons of problems. Work them until you're just sick of it. Okay, just work problems until you're sick of it. You just can't take it anymore. And then you know what you should do after you're sick of working problems and can't take it anymore? Go work some more problems. Okay, so this is how you get through this. You got to work lots of problems. You got to practice. Do the ones in red because they have the answers. And what do you think you should do if you run into a problem while you're working these problems and you're like, you know what, I can't figure this out. What's going on? What do you think you should do? You should probably email me or get on WebEx, and just, hey, we can work it out together. We can work it out together. I would love. Now, there's going to be NASCAR this weekend, so I'll probably be watching NASCAR. I love NASCAR because it's real simple. Left-hand turn, left-hand turn, left-hand turn. I can understand that. And I will stop what I'm doing. I will pause the race, and I will run to the computer in my sketchy pad, and I will help you because it makes me happy. So nothing makes me happier than realizing that you're actually studying and working problems on the weekend. So be sure, to continue doing this on the weekend. So when we hit this on Monday, you're ready to go. All right? Everybody know what you need to do this weekend? All right. Well, I'm going to go ahead and turn off the recording, and let me go ahead and do that. I'm going to stop